Hi, my name is Percy, and I'm an algorithm engineer at DEEP Robotics. As embodied AI getting more and more popular these days, we decided to release a series of videos introducing how to use our robots to do different kinds of research, including locomotion, navigation, manipulation, and more advanced topics like imitation learning and VLA and other stuff. So we are going to introduce some open source classic algorithms and papers, and we're going to show you guys how to implement those on our robots. If you guys want to know more about the code or the algorithm detail, you are very welcome to look at the original paper and the original code. So this video will be the first video of this series. We're going to introduce the ROS2 structure of our system. So the ROS2 structure will be the same across all the platforms, including the M20, the humanoid robots to become, and we're going to release several new robots in the future. So we're going to introduce this ROS2 structure based on the locomotion algorithm of this M20 robot, and let's get started. We'll start by introducing Isaac Lab, installing Isaac Lab, how to use it, and how to use our RL training code on our GitHub repo. Isaac Lab is maintained by NVIDIA. It's currently the most popular robotic simulator around the world, and almost everyone is using that. So let's just get started by installing this Isaac Lab. So we'll follow the official installation methods on their website. It's pretty convenient. First, we'll start by installing Anaconda. Just copy and paste these commands and start installing. After installing, we can upgrade the pip to make sure that you are using the most up-to-date one. Then we just pip install version 5.1.0. This may take some time. So after installing Isaac Sim, we can install PyTorch, Torch Vision, and everything. Just also copy and paste their official command. But the one thing you need to make sure is that if you're using it on Windows, you need to change it to the Windows thing. So you are absolutely installing the correct version. Okay, so after installing PyTorch, we can run Isaac Sim to check whether the installation is successful. This part, so I have already installed some parts, so I can just type Isaac Sim and just run it, and it can just start it. But if you're doing it for the first time, you need to sometimes need to download a lot of stuff, and you also need to kind of like compiling the materials. So you may see that your CPUs is running fully, like 100%, and that may also take a few minutes. So after installing Isaac Sim, we can install Isaac Lab. Isaac Lab is built on top of Isaac Sim. Isaac Sim is basically the simulator. So let's go to our temp folder and git clone Isaac Lab. So after cloning the Isaac Lab, we can just use this Isaac Lab script install to install this repo. Just follow the official commands. And now we can run Isaac Lab to see whether the installation is successful. And as you can see that right now my CPU, like all of my 20 CPU is running full capacity, and this is also normal for you guys. And this may take quite a long time. So just be patient and wait for it to finish. So okay, now we have already started the Isaac Lab simulator. It is installed successful. We can try a small training example. And let us try this Isaac and v0 example. So also just copy and paste these commands, and you guys can see that the code is the algorithm is starting to run and the training has started. So this means that our training part, we have now successfully installed IsaaCLab, and we can use it to train our own tasks, like for the M20 robot. Now we can go to our RL training code. So if you visit our GitHub Center, the DEEP Robotics lab, and go to this RL training, this is where we keep all of our training example code. And I want to explain something here. So the performance of this algorithm is not state of the art, and it's also not we are using here at the company. It is just a minimum implementation of a Locomotion algorithm that you can treat as an example for you to implement your own algorithm. And if you guys are curious about the details of the training code, the deployment code, you are welcome to go to another series for the Light 3 robot, quadruped robot control. And in that series of video, I introduced the details of the training, of the reward functions, of why we set the weight. And I also introduced the details of the deployment algorithm. You guys can check that series for a detailed introduction. So in here, I'm just going to go through this one more time for the M20 robot. Okay, so let's start by git cloning our IO training repo. Okay. So in the installation guide here, we have already finished the first two parts. Install IsaaCLab by following the installation guide and clone this repository. Okay. So we have cloned it, and we can just go to our repo and just copy and paste these installation commands. This pip Python install, and it will just install this IO training repo. And don't worry if there are some bugs or some warning here, it's fine. And then we can list the environments. So currently we only give two robots example here, and each robot we have two environments. It's the Light 3 robot and this M20 robot. So for the Light 3 robot, you can refer to the another series of video, the Light 3 quadruped locomotion control, and that one has very detailed introduction. And in here, we are only going to focus on this M20 environment. So to start the training of the M20 environment is also very simple. Just copy and paste these commands and to the terminal and start running. And it will just start training, okay? So now the training has already started. We can go through a little bit of the output of the training. So we print out almost all the important parts of the reinforcement learning algorithm, starting from the curriculum, the reward function and weight, the termination, like how the robot's going to terminate, and the observation, the actions, and some events here. And events are categorized by when they are going to happen, like for startup or reset. And this is also my current GPU resources. So I currently have two 4090 GPUs here at the company, and I'm going to use that. So if you guys are using the same version of my GPU, you should expect a similar performance of training. If the performance is kind of different from what I show you guys here, you probably have some, maybe your CUDA version is different, your GPU driver version is different. It really doesn't affect a lot, unless there are some problems with your hardware. So if we start training, the speed will be around like a little bit around 1.2 seconds per epoch. Yeah, that is around the speed of this M20 robot training. And if we want to inspect the process of the training, we can go to this logs RSLIL repo to the M20 rough environment, and we can use TensorBoard to visualize the whole training process. Just type these, and we can see the results. So yeah, this will be all our curves, our reward components, and the full reward is just down there. So another thing I want to introduce is that the reward functions here some of them are pretty different from the Line 3 quadruped locomotion algorithm. Why do we do this? Actually, if we use the same set of algorithms, reward components from the Line 3 environment, it can also work and it can also generate pretty good motion. But I want to introduce like different functions that can probably do the same thing. And in the simple tasks like locomotion of this one, it is okay to use just maybe different combinations of them. You can get the similar outputs. But for more advanced, more harder tasks, you may need to pick the functions carefully. You need to think about the problem and what is a good way to describe this problem mathematically. And these functions are mainly adopted from Robot Lab. It's also another open source repo, so you guys are welcome to use that too. Let me introduce the training code a little bit. So I'm not only going to introduce the difference between the M20 training code and the Line 3 training code. If you guys are curious about the details of all the reward functions, the observation action, you can go to our last series to check the detailed training code explanation. So the main difference between the M20 robot and Line 3 is that we have wheels here, and the degrees of freedom becomes 16 rather than 12. So we have 2 degrees of freedom here, 1 knee and 1 wheel. So this will be 4 for 1 leg and 16 for total. So for adding the wheel joint, there are some modifications to the training code. The one big difference is that this joint velocity, needs to, previously we only have the joint pose, because the output of the neural network is the desired joint position of the quadruped. And in here, to control the wheel, we are not using the joint pose anymore, we're using the joint velocity. Because joint pose, when it rotates and moves forward, it's going to be like a very large number and it doesn't make any sense. And we only need the velocity for we to control it to move forward or move backwards. And the main difference is the wheel. So this is for the action. And if we take a look at the rewards here, we also need to make a difference. We need to add some wheel specific reward terms. And the main environment config, we have the leg joint names, we have the wheel joint names. Okay, and let me take a look. And also for the observation, we have this joint pose relative without wheel, joint pose relative without wheel to separate our joint, the other joints from the wheel joint. So this is what we know that we need to separate from the wheel and the joint pose. Another thing I want to introduce here is that the reward functions we used here are pretty different from the Line 3 reward functions, but they are doing basically the same thing for a very simple locomotion policy for the robot to track linear and angular velocity. So like for example, one of the big difference here is that we don't have this base height here. So in Line 3 training code we have the base height. But we don't have it here. But after training, we can still make sure that the robot can traverse at a given height. So how do we do that? We have this joint pose. Wait a second. we have this joint pose penalty here. So this joint pose penalty gives a penalty when the joint pose deviates from the default joint. So as you guys see that when this wielded quadruped moving, the joints, they barely move, right? It just kind of stays at there and the wheels starts to rotate. So we want to penalize any movement different from the default joint. So by doing this, we can also make sure that it traverses at a given height. We don't have to have this base height. So what I want to give you guys an advice here is that to do the same thing, you might have different choices of reward functions. And to choose among them, you need to think carefully about your task. And for this wielded quadruped, it's perfectly fine to use this joint pose penalty as to specify the height. But for a quadruped robot, you don't want to do this because when that robot moves around, the height, the joint pose will have to change. It doesn't have this wheel, it cannot move smoothly on the ground. So these small differences in the embodiment of the robots can result in the difference in reward engineering. So yeah, and there, if you guys look carefully at the other reward functions, they are also kind of different from the Lynx 3 robot. We just want to give you guys different choices for you to choose from. And this code is mainly adopted from the Robot Lab, which is also an open source code base. You guys are very welcome to check that too. And I also increased the desired linear velocity here to 5 meters negative to positive because this robot is bigger than the Lynx 3 robot and it has the wheel, it can move much faster than the Lynx 3 robot. So we increased that. But for deployment, I don't suggest you to use this policy to traverse at 5 meters per second because it's a very simple one. It doesn't have other modifications. It doesn't have any safety consideration. And if you deploy this in reality of 5 meters per second, it's going to be pretty dangerous and it can lose control very easily. Now let's check our training results. So the training has been running for some time here. And these are the reward functions or what they look like. So first thing I want to introduce is these terrain levels. This can specify how good the robot can adapt to uneven terrains. So if you guys can see it goes around 6, and this is actually a pretty good value. It means that it can adapt to pretty uneven terrains. And there are other reward functions here. Let me change to this. And yeah, this is what they look like. They haven't really converged, but honestly, I think we have trained it for 16,000 epochs, and it's actually pretty enough. You guys can wait a little bit more, and the reward is going to be stabilized better. But if you guys see that terrain levels is pretty high, the command level is also pretty high, then it is actually okay. So let's run the results. Let's run the evaluation and see what they look like. Okay, so to play, we can use this. So by default, it's going to select the last checkpoint. And if you want to specify which checkpoint, you can just use a / checkpoint and copy and paste the absolute path to the checkpoint. So we have the training results here, and you can see that the robot is moving around like they are trying to track a very big linear velocity. That's why this error is pretty long. And it can, like this one, it can just go on these uneven terrains pretty well. It knows when to step and when to just roll the wheel and move forward. So after training the results, after seeing the results, playing the results, visualize it, the Isaac Lab is just going to export an Onyx file pretty easily. You just do that automatically, and we can use it to deploy to the real robot. So after copy and paste the policy to this folder, let me just go through the README to see how we can deploy. We can do the sim-to-sim and sim-to-root test using this repo on the M20 robot. So I'm going to remove all the things. Okay, let me just and just compile and source first. So you need to source. You need to install ROS2 here for you to use this package. And I have Humble here, so I just source this and start compiling. So let me introduce the repo a little bit. The DRTDS is DEEP Robotics DDS. We have the data structure support. We have some message here for the joint data command, IMU data, and the M20 SDK deploy is the main deploy folder, main deploy code. We have the deploy logic here for you to safely transfer your policy to the robot and control it. And yeah, it's like pretty standard ROS2 workspace, just had this SRC folder. So we have successfully compiled the whole repo, and to use it, we need to open two terminals here. And in one terminal, we need to open the magical simulation first. So yeah, we need to start the simulation first, then run this deploy code, deploy node. This ROS2 run IO deploy. Okay, just put two folders here. Press Z for the robot to stand up, and press C for the robot to enter IO control mode. And we can use our keyboard to control it, so you can just rotate, and you can also move forward. And yeah, there it goes. Just this is the sim-to-sim part test. Now let me explain the deploy code a little bit. So we are using the ROS structure. So let me run the code and show you guys what the ROS structure will be. So I just quit the remote control because the training and the deployment testing is at my desktop at a company server. And this is my local deploy laptop. And it's going to be more convenient for me to actually deploy the policy to the robot. I can just transfer the policy to it by connecting the Wi-Fi. So in here, we're going to follow the same process again. Let me just source it in one place and source it in another place. So still the same, we need to run the simulation first. Okay, and press Z to enter standout mode, and press C to enter IO control mode. So sometimes there can be some IMU lagging. This is usually because of the laptop. It's not as good as the desktop. It had the system run, it just kind of had this lag. But it's actually totally fine. So you can do the same thing, right? So let me give you guys another terminal to see the ROS structure. We can use ROS2 run RQT graph. So this will be our current RQT graph. And if we use this, we can see we have an IO deploy node, we have a magical simulation node. The magical simulation is publishing some IMU data and joints data to the IO deploy. It gets the observation and it sends out the action. The send out action is this joint command. So yeah, this is exactly what we have here. And we have this topic list. we have these topic lists for battery data, MU data, join command, join data, and if you want, we can also check out the node list. We have these 2 nodes, and if we just run these commands, and we can see that it subscribes to the join command and it publishes these data. And if we use this, you can also see it subscribes to all these and it publishes to the join command. So this is a very simple 2-node structure. One publish the IO deploy, publish the commands, and the magical simulation send back the observation. So I'm going to stop this. And when deploy it to the real robot, we just switch this magical simulation to the real robot. Still, we have an IO deploy node. It's going to publish the join command, but the real robot is going to have another ROS node to receive it, and it's going to send back the real robot data as a join data and IMU data. Now we can begin our SimT real test. So this is the package for the M20 robot. Let's open it. So this will be our M20 robot. And when taking out the robot, I recommend to hold 2 legs, the thigh and the shin together, and ask another person to help you to lift it up and put it on the ground. Okay, now let me introduce what's inside the box. This 2 will be the batteries, and this is the charging hub. And you can notice that there are cable here. You can just put it like this and it will start to charge. And there are some cables for a lot of things. This one is for the charging hub. This one is for the joystick, which is this thing. And there are also some other cables that can plug into the robot. And let me introduce the joystick here. So we have a pretty big one, and if you want to open it, just press this thing. And there are also some cables that can plug into the joystick too. And we also have a user menu that goes with the robot for you to look into it. So when you get a new robot, the batteries are not charged. You need to first charge the battery before you can use it. But for our robot, I have already charged the batteries, so I can start to use it. So let me put this back first. And get 2 batteries out and put it inside the robot. So you need to be careful of the directions. And okay. And just a short click and long click. Okay, so now 2 batteries are on, and the starting button is here. Just press this button, and you will hear that the fans are already starting to rotate and it's making some noise, and the light is shrinking in white. This means that the robot is starting now. Now we can start to deploy our IO policy into the robot. So we have our SDK repo, which is now open on the GitHub, and we can just copy just SCP the files. First, we need to connect to the M20 robot. The password is 12345678, and after connecting to the robot, we just follow the readme command here. Just copy and paste this line of command, so we can copy the src folder transfer it into the robot. The password is a single column, and yeah, now it's transferring the files. Okay, so now we have already transferred the files. Let's go into the robot using SSH. Okay, now we are inside the robot,
and we have this SDK deploy folder we just transferred to. Go to here, and let me just remove all the files to start over again. So before compiling the robot, we need to source the robot's ROS environment. So just do this. And it's starting to compile. So the difference between sim to real and sim to sim is that we need to change this build platform to ARM, because the onboarding compute is the ARM architecture, and my laptop is the x86 architecture. The rest are pretty similar. Okay, so the compiling has finished, and to run the compiled ROS package, we need to use sudo to use the root environment. So you can just copy and paste these whole commands and into the terminal, but let me explain it first. So there are two source command here. We need to source the environment, set up the ROS2 environment. This one is pretty important because we need to change from the default IO control mode to our SDK mode. Those two modes cannot exist at the same time, because if they both send commands to the joints, it's going to be pretty dangerous. And we have this 200 is the frequency here. It's the communication frequency between the robot and the neural network. So this one, it can only be factors of 1000, like 200, 500, and we recommend to be 200, and you don't want to go over it because that would be too fast, and onboard compute cannot stand it. And then it's pretty simple. We just source the already compiled environment and ROS run the package. Okay. So now we have already starting the package, and we can press Z for the robot to stand up and press C for it to enter the IO control mode. So this policy is a very simple policy, and you can do that. You can train this policy following our IO training repo. It's also another repo on our GitHub Center. We just copy and paste a trained policy from that repo and put it inside this SDK deploy. So now we can press WASD and Q and E to control the robot, like it's going forward and backward. And we can also let it to go sideways. Okay, so that was a little bit of tumble here. And let me just control it to turn. Sorry. So this will be what it looks like on the grass and for real deployment. So this will be the end of this video. I hope you guys have fun developing your own M20 robot. If you have any question, you can contact the after sales service team, or you can join our Discord and post ask us there, or you can just post an issue on our GitHub. Thank you.